This is part 5 of the video series on global optimization. In part 4, I describe my version of the Conical algorithm to solve the minimization of a concave function over a polyhedral set. It has the desirable property of converging in a finite number of iterations, producing the exact optimizer of the program. In this video, I will describe in detail the proof of finite convergence. Remind you of the assumption that we have made so far when we described the algorithm in the previous video. So we are trying to solve this problem, the minimization of a concave function over a polyhedral set. The first assumption we made is that this polyhedral set is bounded, so this minimum exists. So we call that alpha star is the minimum and x star is the optimizer. And also we are assuming B to be strictly positive. In other words, the polyhedral set that we have is non-degenerate. And also another assumption that I have added is that the level set defined like this, the set of all x such that f of x is greater than some number alpha, any alpha, those sets are bounded sets for fixed alpha. And the reason we did this is because remember when we did the alpha extension, we were looking for the maximum x such that f of x is greater than some number. So we need that maximum to not be plus infinity, to be a finite number. So we need to assume that the level set, these are called level sets, those are bounded. So at iteration q, we have an mq, that's our set of cones to be searched, and also we have the best solution that we know, alpha bar q and x bar q. This is our best solution that we have at iteration q. Now the first thing that we do here is that alpha star, this is a trivial fact, is less or equal to alpha bar q plus 1, less or equal to alpha bar q. Right? Alpha star is less than this because alpha star is the minimum, and this is a feasible solution, so it has to be less or equal to. And by construction of this sequence alpha bar q of the next iteration is always less or equal to the previous one. So this alpha bar q is a decreasing sequence bounded below. So the limit of alpha bar q exists, and let's call this alpha bar. And of course alpha bar is going to be greater or equal to alpha star. Okay, so this is a trivial fact. Now, so the algorithm now, if you look to the tree of the algorithm, it starts with one cone, it's going to subdivide it into some cones, and then we take one of those cones and subdivide it, and so forth. So the algorithm is going to generate sequences of nested cones. Each cone is obtained from the previous cone via the algorithm. So let's assume that one of these sequences is infinite. So for the next two lemma deals with the instances when those sequences are infinite. So I'm going to see let c ik equal to c of z1 ik, etc. zn ik. This is a sequence, and let's for a moment assume that is an infinite sequence. Okay, it never stops. Okay, by the algorithm. In other words, and the way it doesn't stop is because the LP, when we solve the LP, the maximum is always bigger than 1. So this is maximum of E transpose HIK minus 1 x subject to AX less or equal to B x in I and CIK. Okay, so we have this. All right, our maximum is always, when we solve the LP, we found that the maximum is always bigger than 1, and that forces us to subdivide the cone CIQ into smaller cones. Okay, and let's assume that this is true. Then lemma 1 is that this cone is going to converge to a single ray, just like when we address the exhaustiveness. So the limit of z j I k is equal to some z star for k going to plus infinity, and this is true for j equal 1 till n. Okay, so all these z's that defines the cone collapses to a single point. Okay, so the proof is quite simple. So we're going to do let v be a vertex of our original let v be a vertex of our original region, the set of X of our polyhedral set. Okay, and assume for a moment that v is the optimizer. In other words, max of E transpose HIK minus 1 X, and here AX less or equal to B well, it's implicit that it's over this set. This is equal to E transpose HIK minus 1 times V, and V belongs to CIK. Okay, so when we solve this problem, we found out that the optimizer is this vector, vertex V. So what does the algorithm does in that instance? The algorithm will split this cone CIK through the vertex V. Okay, so V becomes an extreme ray of the next cone, right? Of C of I k plus 1, right? C of I k plus 1 is one of the subcones, and V becomes an extreme ray of that. Now, if V belongs to CIL, for L bigger than K, any L, then V, an extreme ray of CIL, right? Because CIL is contained in CIK plus 1. So therefore, if V is an extreme of the bigger cone, it must be an extreme ray of the inside cone. Okay? And so therefore, and then if I draw a picture here, and here's my CIL, right? This is CIL. And remember, and V is an extreme ray, right? So V is one of these points, right? Here, in this case, n equal to 2, I have two extreme rays, this one and this one. I'm sorry, not this point, not this one. I meant this one. So it has this extreme ray and this extreme ray. And remember when we did with the algorithm, what we did, we extended this V, so this is Y1, and then this is Y2, and then we form the plane like this. So this V is under the plane, right? So therefore, in here we have E transpose H of IL minus 1 V less or equal to 1. All right? Just like in this picture, it has to be less or equal to 1. And therefore, V is not an optimizer. V is not an optimizer of the LP at iteration IL. Of the LP at iteration IL. In other words, V is never going to repeat. So in here, V was the optimizer, and then after that it will never come back, it will never repeat. All right, and therefore, and since our polyhedral set X this polyhedral set, we know from the composition principle, from the composition theorem, that any polyhedral set has a finite set of vertices. Right? Any polyhedral set has a finite set of vertices, and therefore V the algorithm will never split. We never find a vertex as the optimizer of the LP, and therefore that cone will be split using the exhaustive subdivision process. All right, and because we split the cone using the exhaustive subdivision process, then this result follows. Okay, it's quite simple, and therefore the version of my algorithm essentially, after a certain number of iterations, it becomes the Tuy-type algorithm. Okay, so now let's assume that we have an infinite sequence defined by the vector z1ik So this is an infinite sequence of nested cones obtained via the algorithm, which means that one, at every iteration, one is strictly less than the maximum of E transpose HIK minus 1x subject to AX less or equal to B and X belonging to CIK. All right, that's what makes it infinite. So we never got less or equal to 1. And let's call this gamma IK, the value. Okay. Now, lemma 1, we know that ZIK, let's say GJIK, converges for k going to plus infinity to Z star, right? For j equal 1 till n. That's, we got it in lemma 1. Now we want to prove another lemma, lemma 2, that the lower bound of CIK converges as k goes to infinity to some number, let's call it L, and which is greater or equal to alpha bar. This alpha bar here, which is the limit of the alpha bar Q. And let's prove that. Now, I'm going to just note that IQ, I'm just going to call it Q, so that we don't have to carry on these indices like this. Okay, so now I put in a picture here of what's happening. So this is case n equal to 2. Okay, so here's my cone CIK, right? And the green region, this is the feasible region. This is Z1, Z2, and then this is delta Z1, delta Z2, the point on the boundary. And then we alpha extend it to Y1, Y2, and so this is this first line, that's the Tuy hyperplane. And then we maximize over the feasible region, and we obtain this plane. And I'm calling this VQ. Okay, so let VQ the optimizer of the LP. Okay. In other words, gamma Q, that's equal to E transpose HQ minus 1 times VQ. All right. That's the optimizer. And also, I'm going to join 0 and VQ to get V bar Q that cuts into this plane. So V bar Q, that's just 1 over gamma Q times VQ. Right? So from here you get E transpose HQ minus 1 V bar Q, that's equal to 1. Okay. Now, so this says that V bar Q is equal to sum of I equal 1 till n of lambda I comma q times yiq. All right, and here E transpose lambda q equal to 1, lambda q greater or equal to 0. Right? Because V bar q belongs to this n minus 1 simplex, then it is a convex linear combination of the y's. Okay, remember the y's here, the yi. How we got yiq, that's the alpha extension of delta of z1. Right, y1 is the alpha q extension of z1. So yiq is equal to theta iq times delta of z1 ziq. Right, and this delta, that's greater or equal to 1. The y is always on the other side of delta of z. Okay, so now this converges to, remember that our level sets are bounded. We created the y's, we went as far as we could on this line, but bigger than alpha bar q. So this theta iq are bounded, and of course the delta ziq converges, since the ziq converges to z star. So this converges to theta I delta of z star, and this is greater or equal to 1. Okay, so we have this 2 now. So we plug this in there. So V bar Q is equal to the sum of I equal 1 till n of lambda iq, and then I plug in for yiq, so theta iq delta of ziq, and of course E transpose, understood that E transpose lambda q is 1 and lambda q greater or equal to 0. So the lambda q belong to a bounded set, and delta of ziq converges, and the theta iq also converges subsequently. So V bar q converges as q goes to infinity to the sum of I equal 1 till n of lambda I, right, times theta I, and this converge, they all converge to the same point, delta of z star. And of course here E transpose lambda equal to 1, lambda greater or equal to 0. So this is some number, let's say some number theta times, not theta, I already used. So let's say psi times delta of z star. And of course, here psi is greater or equal to 1. But V bar Q is a feasible point, right? Because VQ is a feasible point and 0 is a feasible point. So any point on the line V bar Q is a feasible point. So psi delta of z star is feasible, right? But psi, but delta of z star, remember, is we went as far as we could till we hit the boundary of the feasible region. So this means that psi is equal to 1. Okay, it must be equal to 1. Okay, so now, since psi is equal to 1, so we showed that v bar q then converges to delta of z star. So here, we just showed that v bar q converges as for q to delta of z star. And here, subsequently, if necessary. Now, the same thing holds for VQ. Why? Because VQ is equal to gamma Q times V bar Q. All right. So, but VQ and V bar Q, VQ belong to the, it's a feasible point, so it belongs to the set of X such that AX less or equal to BX greater or equal to 0. Right? So it's a bounded set. So therefore VQ converges subsequentially and V bar Q also converges subsequentially. So gamma Q also converges subsequentially. And then, so we have VQ converges as Q goes to infinity to some number, let's say gamma, times, and V bar Q converges to delta of Z star. And of course, gamma is greater or equal to 1. Right? Because gamma Q is always bigger than 1. Okay, so with the same reasoning as we did for V bar Q, remember by definition of delta Z star, there is no other point beyond delta Z star that's feasible, and therefore here gamma must equal to 1. Okay, and therefore VQ also converges to delta of Z star. Okay, so far we have shown that VQ and V bar Q, they both converge to delta of Z star, and also gamma Q converges to 1. Okay. Now, let's look to the lower bound now. How is lower bound created, right? So let's HIQ, that's these points here, where it's maximal. So that's nothing more than gamma Q times YIQ. All right? So therefore, the limit f of h of IQ this limit here, limit over Q, because of continuity R function, that's just the equal to the limit of Q of gamma Q YIQ, right? F, which is equal to then, by continuity is equal just to the limit of Q of gamma Q, and then times the limit of a Q of YIQ, right? So this is 1, right? Subsequentially if necessary. And so this is just equal to F times the limit Q of YIQ, right? But the YIQ, remember how the YIQ are created. F of YIQ is equal to alpha bar Q. That's how they were created. Okay. So in the limit, so when we do the limit, this is just equal to alpha bar, right? So for I equal 1 till n, and this is true for I equal 1 till n. Okay, the function value of the h's, these points here, they all converge to alpha bar. So now, how is the now let's look to the lower bound. How's the lower bound from the previous video? The lower bound of CQ plus 1 was set equal to the maximum of the lower bound of its parent, which is CQ, right? And then the minimum of f of HIQ I equal 1 till n. Okay? That's how we created the lower bound for the next cone. We just took the lower bound of the parent cone, the one that was subdivided, and then we took the minimum of these h values. So this is, you refer to the previous video for this. So this says two things. One is that the lower bound of CQ is less or equal to the lower bound of CQ plus 1. Right? Because CQ is a mass, so it has to be greater or equal to this. So therefore, this lower bound of CQ, these lower bounds, it's a monotone sequence, right? And it is, remember by definition, this is just less or equal to the minimum of f of x subject to ax less or equal to b and x in CQ plus 1. That's by definition. It's a number that we created that is less than the minimum of this. But this is, I could say that this is less or equal to the maximum of f of x subject to ax equal to b, x greater or equal to 0. Right? I could say that. That's a trivial inequality. So therefore, lower bound of CQ is a non-decreasing sequence bounded above by this. And therefore, lower bound of CQ converges, when Q goes to infinity, to some number L. Right? And now, also, from this also tells me that the lower bound of CQ plus 1 is greater or equal to the minimum of f of HIQ I equal 1 till n. Okay? Just from this relation here, this equality here. But we've shown that the function value of HIQ, they all converge to alpha bar. So by taking this limit on both sides, then I get L. We've just shown that it converges to L. L is greater or equal to, and this, they all converge to alpha bar. So this is converging to the alpha bar. And therefore, we just prove this lemma too. So, theorem called theorem 1, which is infinite convergence. That alpha bar is equal to alpha star. In other words, remember the alpha bar Q is the best solution that we have at iteration Q. Then if we keep iterating long enough, then alpha bar is going to be, the limit is going to be equal to alpha star. Okay, so that's the infinite convergence. So the proof so let V star be an optimal vertex of my feasible region x such that ax less or equal to b, x greater or equal to 0. Okay, we know it exists by concavity. We know that this exists. We can find an optimal solution at the vertex by concavity. So because, remember the tree of the algorithm, we start with one cone, we split it, and so forth. So V star is going to belong to a sequence of nested cone. So let CIK sequence such that V star belong to CIK for every k. Okay, it has to. We have to, we're going to find a sequence that V star belong to every member of that sequence. All right, so case 1, so there are 3 cases. Case 1, this sequence is infinite. Just like we did in lemma 2. Okay, so therefore the lower bound of CIK, right, we know that it converges to, for k to infinity, to some number L greater or equal to alpha bar. But what is the lower bound? The lower bound of CIK. That's less or equal to, by construction, to the minimum of f of x subject to ax less or equal to b and x belonging to CIK, right? By construction. But V star belong to CIK, right? So I could say that this minimum is less or equal to f of V star. And V star is optimal, so this is equal to alpha star. Okay. So now, taking the limit of CIK, then I get L less or equal to alpha star. But L was greater or equal to alpha bar. And therefore, alpha bar is less or equal to alpha star, and alpha bar greater or equal to alpha star. So this implies that alpha bar is equal to alpha star. And that's the proof in this case. Okay, now case 2. The sequence is finite. And there are 2 ways it could be finite. So in this case 2, we say there exists big K such that E transpose HI big K minus 1 X, the maximum, the LP, the maximum of E transpose H of I big K minus 1 X subject to AX less or equal to B, less or equal to B, and X belonging to CI big K. When we solve the LP, we found that this is less or equal to 1. And from the previous video, that means that every X such that AX less or equal to B, X belonging to CI big K, remember this, for every X such this, f of X was greater or equal to alpha bar IK. All right. And since V star belonging to Cik, then I have f of V star is greater or equal to alpha bar Ik. Okay, and this is alpha star. Okay, but my sequence alpha bar Q is always bigger than alpha star. So this implies that alpha star is equal to alpha bar Q for every Q greater or equal to I big K. So my sequence is constant equal to alpha star, and therefore in the limit alpha bar is equal to alpha star. All right? So case 3, we're assuming that the sequence is finite. That is, there exists a big K, such as Ci big K, the last cone in the sequence. All right? How would that happen? That means that for every Q greater or equal to I big K, right, Cik belong to MQ, right? But there is another cone, there exists another cone CQ belonging to MQ, and CQ was picked. Rather than Ci big K. Okay, so this sequence is finite not because the LP, the maximum in the LP was less or equal to 1. It's just because Cik belonging to the cone, to the set of cone MQ to be searched, but we always found another cone to pick rather than this cone. That's why this sequence never continued. Well, let's see, how do we pick a cone in the algorithm when we describe the algorithm? I gave 2 criteria. One was the age criteria. Remember, we look at MQ and then we pick the oldest cone. But Cik, this cone, it's a fixed cone in the tree. It only has a finite number of cones older than it. So this can never happen. This here, that cannot happen with the age criteria. Okay. Now the other criteria was the lower bound criteria. Remember, for the lower bound criteria, we look to all the cones in MQ, right? And we pick the cone that has the lowest lower bound. So if we translate this statement right here, that means that for every Q greater or equal to I big K, there exists a cone CQ belonging to MQ such that the lower bound of CQ was less or equal to the lower bound of Ci big K. There was always a cone in MQ that has that its lower bound is less or equal to Cik, and that's why this cone CQ is picked. Okay. But now this lower bound Cik, remember, V star belonged to Cik, right? So this is less or equal to f of V star equal to alpha star. So I have therefore an infinite set of cones CQ such the lower bound of CQ less or equal to alpha star from that tree. From that tree, then I'm going to pick sequence. So therefore there exists a sequence which I call CJK, sequence of nested cones, an infinite sequence, I should say, an infinite sequence right, of nested cones just like in lemma 2, all right, such that the lower bound of Cjk is less or equal to alpha star for every k. Right? Now if we take the limit, we know from lemma 2, so this is lemma 2, so this converges to some number L, right, which is greater or equal to alpha bar. That's what lemma 2 says. And this, of course, L is going to be less or equal to alpha star. So therefore, alpha bar is less or equal to alpha star, and alpha bar is greater or equal to alpha star, and therefore alpha bar equal alpha star. Okay, so in all cases we showed that the limit, this alpha bar, has to equal alpha star.